Hello everyone, this is the tutorial of the week 11 where we are going to discuss more details about the BFS and DFS, which are very popular in simple algorithms for traversing graphs. So let's start with the BFS, the breadth first search. There are several applications in industry, in the real world, for the BFS. For example, web crawling, when we want to find all the pages starting from a certain web page and then following links after that web page. Another application is on social network. For example, imagine Facebook. You have a person, and this person has a group of friends, and each friend knows a group of friends, and eventually you'll find, or you get to find someone who you don't know. So then you are in a good position to recommend this person as a new friend to the starting person. Another application of BFS is garbage collection. So we start with a process. The process has threads. Each thread has several objects. Some objects call another object, contains other objects, so on and so forth. And eventually, during the execution of a program, some objects are left alone, are no longer called, referenced by any process, any project, or any process, any thread. So a BFS can be used to identify such objects and free the area of memory. BFS is also used in logic, several applications in logic, and also in games. You can imagine, for example, solving a Rubik's game. When you start from a certain game state of your cube, your Rubik's game, and then you have possible actions, action 1 to action n, leading to any possible game states. And each game state are the actions leading to other game states. So eventually a BFS could find, is a bit computationally expensive, but a BFS here could be used to find the optimal path to a solution, a game state which is a solution. So these are not everything, it's not everything, but these are some of the applications. For example, you can imagine in robotics, if you want a robot, an arm that makes the minimum number of moves to get one certain piece and pile this piece. So how to find the minimum number of moves? So you can imagine a BFS where you have a starting state of the problem, and then each action or an edge in this graph is an action. For example, move, rotate, go up, go down, and you are trying to find the last state. In this case, it's the state where this brick is on this pile. So BFS could also be used in this application. So it's a simple algorithm that has plenty of applications. Let me just share with you another application of the BFS. This one was more famous, or relatively famous. It happened in 1959. It was a project in IBM headed by Arthur Samuel. So what is interesting in this project and how it relates to BFS? Basically, in this project, Arthur Samuel and his team managed to use BFS to play checkers. So if you know checkers, it's like chess, but you don't have the different pieces, you have just one single piece that moves diagonally. So just moving diagonal. So you are probably familiar with checkers. And in this case, you start with the game state, then you have the possible moves you can execute, leading to other game states, in each game state there will be options of actions for each game state. Very similar to the Rubik's game solution, but in this case we are not looking for the solution because the tree will grow very fast. So he also applied some statistical methods with similar ideas of machine learning to evaluate game states. So create an evaluation function for game states to assess how good or bad for the machine player, the bot, how bad or good this state was. So based in this function, for come up with this function, it analyzed historical data. So it was a basis using basic ideas presented in machine learning. And in the result of this project, as a result, they managed to beat some top players, top human players. So it shocked the world at the time that computers, not computers because computers didn't exist, but machines could beat human players in a game. So using simply BFS, some statistical models that resemble machine learning, and also, yeah, and evaluation functions. So BFS are really cool algorithms. If you want to know more about the story of Samuel, if you want to know more about the story, you can just Google it, try to find Arthur Samuel, and you will find information about his project Computer Checkers for MIT and about the results. So here you have a game tree, and just it's a different game, but the idea is the same. So, and you keep pruning because you keep cutting the tree because you cannot grow the tree to its completion. So I really recommend this story as a really nice background. Now let's remember the algorithm, the pseudocode for the BFS that you have seen in class. The algorithm is very simple. It starts with initialization. So initialize the distance from each vertex to the source as infinite. Its color is white, it means it has not been discovered by the algorithm. And the predecessor is nil. Then you set the root. Then you have a data structure here, 5 for data structure. First in, first out. So in this case, you insert a node in the queue, in this case the root node. An interesting thing about this data structure is that each vertex in the graph will be inserted, will be queued, and queued only once. Also, we see here a for loop in lines 20 or 12 to 17, and the number of iterations of this loop is upper bounded by the number of edges. So it's upper bound by the number of edges. If the graph is, in this case, the graph is not directed, so it will be 2e. And once you visit the adjacent vertices of the current node, the U node, the U vertex, once you visit, you discover all the neighbors of the current node, you set the color to black. So if we sum the runtime of this algorithm, we have big O v plus e, the number of vertices plus the number of edges. In this side of the slide, we see an illustration of how the BFS works. So hopefully you are now familiar. You have seen lecture how the BFS processes. Basically you start with the starting node, then you create a frontier. It means the next, in this case we have just two, so the next level. You don't visit the nodes in V plus 1 before you visit all the nodes, all the vertices in the level D. So in this case, this is the level D, this is the frontier. We don't discover all the vertices before we discover these two. And this is what will happen here. So they are discovered, they become gray, but we still don't know if they have other vertices connected to them. And then this node is set as black, so it's like exhausted. Then we start with W. Why do we start with W and then after R and not the other way around? R and then W. So pause the video and try to answer this question. Why do we start with WR? So W is the first one that we will visit its adjacent vertices and not RW. So hopefully you answered the question correctly. It's because the adjacent list of this graph. So the adjacent list of the vertex S, the first one is W, the next one is R. So that's why W appears first. If we are talking about adjacent matrix, so the indexing of the vertex W occurs before the index of the vertex R. So we continue proceeding, we exhausted this one. We will not visit or we will not investigate this further before we investigate R. And this is what happens, so on and so forth. So I leave you a last task regarding the BFS here. It's build the adjacency list of this graph using as an input the sequence in which the vertices are discovered and exhausted. I mean by exhausted, set the color as black. Next slide contains a question: in which circumstances the standard BFS cannot find the shortest path in a graph? Because if you remember from the previous slide, the BFS is totally capable, in this example, to return the distance between the starting node and any vertex. The distance is the number of edges separating this node, the starting node, to each vertex in the graph. So in this case, the BFS succeeded. Why does in this case it does not succeed? The answer is obvious, because this is a weighted graph. So in this case, how can we solve this problem? The shortest distance between V2 and V5, for example. If you use this on the BFS, the shortest distance is this one. But because there are weights in the edges, this is the shortest distance. So how to solve this problem? There are several ways of doing so. For example, and there are also several problems. One problem is the single source and shortest path problem. You also have the opposite way, the single destination shortest path, single pair shortest path problem. So you have a pair V4 and V8 and you need to find the shortest path, and all pair shortest path. So for each pair of vertices, the shortest path. So there are some algorithms, some of them we will investigate in this course, most of them. So you will examine this problem in the next weeks. Another exercise: show the distance and the predecessor values that result from running the BFS on the directed graph, figure A, using the vertex 3 as a source. So you are asked to provide the distance and the predecessor. Here is the adjacency list. So try by yourself. Pause the video, try by yourself, and then compare the solution. So here's the solution. An interesting thing is that not just the vertex, the root, the source has predecessor new, but also the vertex 1. Well done if you have done it. Another exercise argued that in the BFS, the value of the distance assigned to a vertex u is independent of the order in which the vertices appear in each adjacency list. So for example, in this case, the distance between 3 and 6 independent if 6 appear before or after 5. So the answer is the BFS does not assume any particular preference or any particular order between these two vertices, and they will have the same distance because we don't visit the other vertices before we exhaust these two. And the second part of the question, using the figure 22.3, it's not this one, the next slide, show that the BFS tree computed by the BFS, here's a concept that we need to explain, can depend on the ordering within the adjacency list. So what is the BF tree computed by the BFS? It's basically the tree that can be obtained from the predecessors. So you follow the predecessors, so you will have a tree. And why the distance does not depend on the adjacency list, the BF tree does depend. So you should answer using this figure, but we can think of a simpler example. This is a simpler example just to illustrate how the adjacency list can affect the BF tree. So let me change the color. In an adjacency list where A appears before B, the Q starts with S, so let's examine S and Q. Then what are the adjacent vertices A and B? So A and B, so S is the predecessor of A and B. Now we will the QA. What are the predecessors of A, or the adjacent vertices of A? C. So C will be, C's predecessor is A. Then with the QB, but B doesn't have wide adjacent vertices. Then with the QC, and we finish it. And it's obvious that in the case where the adjacency list where B appears first, we will have this BF tree. So this is a BF tree. Where B appears first before A, and this is also BF tree where A appears before B in adjacency list. So again, why the distance does not depend on the adjacent list. The resulting BF3 depends. This is a simple example. You could try to find the same example in this larger picture. Let's now talk about the DFS and starting with some applications. It can also be used for solving puzzles that require a single solution. So for example, while the BFS finds the shortest path between a starting vertex and any other vertex, the DFS does not necessarily find the shortest path, but it finds a solution. And there are some trade-offs regarding performance concerning performance in terms of memory and also the speed. But the fact is that DFS can be used for solving puzzles or problems that you don't need to find all the solutions but one single solution. There are also applications in the real world, like for example train rescheduling during traffic disturbances. So in fact, when to use BFS DFS depending on how optimal you want to be. Depend on this, among other circumstances like the characteristics of the graph, the level of in degrees and out degrees of the vertex, also the characteristic typology, the structure of the graph, general structure of the graph. We will talk more about the structure of the graph in this tutorial. So let's start talking about some general characteristics of the DFS. You keep exploring the first vertex, you keep exploring, let's say going down the tree. It's not exactly the tree because it's a graph, so you keep exploring the first vertex until this vertex, there is no other white vertex that you can visit from this one. So in this case, you backtrack, you go to the previous one, and from this previous one, you visit the next vertex. So in this case, then you are backtracking. So you backtrack here, and then after you backtrack, you run a DFS again. So this is the general idea of the DFS. Similarly, we talked about the BF3. So one connected concept is a DF tree. So then you also have a DF tree, and not just one tree. You might have a forest. We saw an example of a BF forest in one of the solved problems. And another information is about the timestamp. For each vertex, there are two timestamps. First is when the vertex is discovered or it becomes gray, and the second one when it's finished. When you finish searching all these vertices adjacent list and V becomes black. Now let's take a look at the general structure or general procedure of the DFS. Now let's take a look at the pseudocode of the DFS. Again, it's a very simple. You start initializing the algorithm, the graph, setting the color white and the predecessor new, and also the time. This will be like a ticking clock. It's like a ticking clock of our algorithm, which will be used as a timestamp. So every time we change a vertex, or we discover, or we black this, or change the color to gray or black, so this ticking clock, this time will be incremented. Then we visit all the vertex which are white, we apply for each vertex which are white, we visit using DFS. DFS visit is a recursive function. You see it again here, invoking this function. And what we do, we basically set the current vertex to gray, signalizing that we discovered. And if the first vertex, we try to identify the first adjacent vertex, which is white. Why? Because this one, from that one, we will apply this recursive function. We will apply a DFS. If that's no longer possible, so we set the vertex black and increase time, set the time of finished as the ticking clock. The complex of initializing the graph is big O V, obviously. And again, the loops of 4 and 7, there are several recursive calls, but the aggregate costs of the loop 4, 5 of lines 4 to 7, the aggregate cost of all the recursive calls will be big theta of E. An interesting fact, a comparison between DFS and BFS, where the DFS is big theta V plus E, BFS is big O V plus E. So this difference is because the DFS might start several times to discover all the vertices, but the BFS might not discover all the vertices. So we cannot affirm this. The BFS, we cannot affirm this because we don't know about the lower bound of the BFS. We have no guarantee about the lower bound of the BFS. So we just provide the guarantee of the upper bound. An interesting analogy of how the DFS works is a labyrinth. So I don't know if you have ever been in the garden at the Palace of Versailles, somewhere near Paris. So imagine someone falling in a parachute and falls here. Then this someone will try to find an exit. Oops, it's not here. Let's say it's closed. So this person backtrack, walk backwards, and then try to find the other pathway. But then it's closed. Oops, it's also closed. Try to find another direction until eventually find. Let's say this person backtracked all the ways possible and none of them could find an exit. So another person falls from parachute to another place and then start again. So I think, if I'm not mistaken, this is Versailles. So it's just an interesting analogy how the DFS can find your way out of this graph. If you map this labyrinth as this maze as a graph, so you can apply DFS. DFS is, which one is more appropriate, DFS or DFS or BFS? But when you want just to go out of the place, just get out of here, so you don't want to find the optimal way or the best way from every possible starting point. You don't care about it. You just want to find the first one that works for you. So the DFS here is probably is a cheaper solution for this particular problem. We mentioned about the structure of the graph. So the performance of DFS will depend on the general structure of the graph. How can we describe the structure of the graph? In terms of the edges, because there are some taxonomy for the edges. There are some categorization for the edges. There are tree edges, back edges, forward edges, cross edges. Tree edges is basically what we find using the predecessor of the vertices. So it resembles, these are the deep first forests. resembles the BF tree as well. So we have a DF tree. The back edges. The back edges are okay. Let's say this is a tree edge. This is a tree edge from UV. And then if you have another edge, this is direct graph, another edge going backwards to a vertex that you already visited, this is a back edge. A forward edge, let's say you have this one. So this vertex was not visited at first, this one was visited first, but this is a tree, this is a backward, this is a forward. And you have cross edges which are none of them. So it's possible to describe the general structure of a graph using this definition. Probably you can infer if the DFS is the most suitable algorithm for using for your problem. So here, an exercise, classify the edges in the graph below. So this is the starting out. So this one is easy. So you investigate Z, then I guess you investigate Y, then you investigate X, then you backwards, you backtrack, then you backtrack, then you investigate W. There is nothing else you can do from here because you're backwards Z, you're backwards S, and there's nowhere you can go. Then the graph starts again, let's say from T, then visit V, then you can go to W, but W has been visited, it could go back to S, but S has been visited, so there is nowhere to go. Then backtrack, then visit U, nowhere to go, backtrack to T, there's nowhere else to go. So which ones are tree edges, back, forward, and cross? Now the next exercise, give the visited node order for each type of graph search starting from node S and giving the following adjacency lists. So you have here, this is the adjacency lists. What will be the order in which the vertices will be visited using BFS? And what is the order of the visited nodes using DFS? So I'll give you some minutes, you can pause the video, try it yourself for some minutes, and then see the solution. So here's the solution. And finally, the last exercise of this tutorial, update the BFS algorithm so that every vertex V in the graph contains not only the distance, we were using this notation in previous examples, the length of the shortest path, so this is this is the length of the shortest path from S to V, but also the number of different paths of that length. So the second part here, how do we answer this? How can we change the BFS algorithm to contain not just the distance but the number of different paths of that length? So pause the video, take a look at the BFS algorithm, and try to find how the minimal is a minimal change, but how can you change it to get the number of different paths? So here's the solution, and the main difference is here. So let's say for each vertex V, when going uh, from U to V, so for each vertex U. So here's the solution. So imagine that you have vertex U going to V, and if V is white, it means it has not been discovered. So how many paths of that length we have from U to V? We know that U, let's see, U dot M, no, number of paths. So U dot N, number of paths. It's a bit confused. U dot N is the number of paths to U. So how many paths we have to V? Obviously the same, right? And they will be the same, because if there are X paths to U, so the same number of paths, there will be the same number of paths to V. But if V is not white, it means the previous vertex already discovered. It was already discovered through a previous vertex. So in this case, what we have is that the number of paths to this vertex is the sum of the previous result plus the new number of possible paths. This was equal to a dot n in the beginning, but then we found out that u dot n, the vertex u is also passed to v, and then u dot n, you add u dot n to this number. There's a little condition here, and I leave to you to find out why this condition is necessary. So this was the tutorial for today. We talked about BFS and DFS, the overall complexity of both big O V plus E. For the DFS is big theta. So, and also some applications. They are very simple algorithms. So I hope that you could enjoy everything. You could understand. So bye bye. Take care.